this thing at 2 comma what? 16. How'd you get 16? Plug 2 into the height function and you get 16. That's correct. And you're going to 2.5 comma something, 2.1 comma something, 2.05 comma something, and 2.01 comma something. How do you get all these values right there? You plug them into the function. Now on your calculator, that's something you're going to need, that you should do. You shouldn't waste your time trying to do it otherwise. The easiest way to do this is to plug in the actual function, which you can't see right now. You plug in the actual function. What is it? 40 minus what?
Minus 16x squared.
X squared, like this, right? And what we did is if you plugged in, if you do vars y1, if you evaluate it at 2, what should the answer be? Oh, it is 16, right? So now what does this allow you to do? You do second entry, and instead of 2, what do you plug in? What? 2.5, right? It's 0, right? And then what do you plug in? Oh, quit. Then what do you plug in? 2 point what? 2.1. So you can do this one by one, right? Second entry, 2 point what? 01, I think it is. Is that correct?
Where's the y1 key? 2.0.
Ah, y1 is under vars and then function. Vars and then function.
Is there any quicker way?
Points we're going between. 216, and what's the next point? X comma what? 40x minus 16x squared. This is the first point, and this is the second point, right? And what are the x values we're plugging in? 2.5, 2.1, 2.01, and I don't know, 2.001? 0.05, thank you. 2.05, correct? If we were just going to generalize this using those 2 points, can you tell me what the slope is between those 2 points, just written like that with x's? 16 minus what? 40x minus 16x squared over 2 minus x, right? This right here represents the slope between p and q, where q is any point on the function. Any point on the function. So what can we now plug into our equation up here? Everybody pause for 1 second. Put your calculators down. Put your hands up like I'm sticking you up at the bank teller. Great. Okay, hands down. Don't touch your calculators. This is y1. This is the function value. We're going to write an equation for the slope. We know what that should be. It should be this thing right here. Should we simplify this a little first? We can. What is this one on? What is that right there? On our calculator, what have we written that in as? That y1. So you can actually write that in as y1x on your calculator. We just need to be careful about our parentheses. So if we actually do this with parentheses properly, you end up with, and this is the slope function, remember, what was it? It was 16 minus y1, right? Do you understand what I just did there? Instead of writing out y1 again, what did I type in? y1 evaluated at x. What is y1 evaluated at x? 40x minus 16x squared. This makes it so you don't have to type the same thing out again. How often, have you ever made a mistake with parentheses on your TI calculator? Everybody has, every day. Minimize it. So that's the numerator. What am I dividing that by? What was it? 2 minus x. So we're dividing it by 2 minus x. We're not going to look at what that function looks like, but we're going to make a table. So let's go back and look at our table. We're looking at the same values. What do we get here? Take a look at this, everybody. What was the first column? What is y1? Y1 is the actual what? Function values. Y1 is just f of x. This is the function right here. This is what we're looking at. These are all of the slopes. And we were trying to find the slope at what? The instantaneous rate of change at 2, right? Can you plug in 2 into this equation right here? Why not? It would make it 0, right? So you look at the values around it. What do you notice? Does it look like it's going to the same value from both sides? Yeah, so we look at maybe the immediate vicinity. We look at these two. We look at those two, right? It looks pretty good. You could add them and then average them, correct? What does it look like the value actually is? 24? Negative 24. Looks like it's exactly negative 24. Could we get even closer with our table if we wanted to? Yeah, we could. What would we change here? We would change on our calculator the table set 1 point, how about this? 999 and 0.1231. Is that pretty close? Take a look at this thing. Now, negative 24 at that point. What does that actually tell you? What's the calculator doing? Be more specific. You said it over there. It's rounding. Can the calculator store an arbitrarily long decimal? No, the calculator internally rounds. At a certain point, it'll start doing this. Is that a pretty good indication that the actual value is negative 24? Yes, that's a very good indication. That's great. You also need to be very careful, though. Sometimes your calculator will lie to you. Just always be very. Does that kind of make sense based on what we saw before? Yeah, it matches our guess. That's a good thing. Have I given you the tools to prove that that's the actual rate of change at that point? No, but is that a pretty good estimate? Are you pretty sure it's actually negative 24? Yeah. When your calculator pumps out something like that, or it pumps out it's negative 24, what? Its velocity, what's it going to be? It's, anybody know? It's in the question. This is a velocity, and what are the units? It's feet per second, thank you. It is feet per second.
Same thing with like
All of them? Yeah. What zoom should I use? Nope. Which zoom option should I choose? Calculator's down, hands up. What zoom option should I use? Nope. 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 No. Zoom trig. It makes marks at pi over 2, which is really nice. And look what happens here. Okay, so it's going berserk in the center. You don't really care about that, though. You're trying to find the slope of the tangent line at 1, 0. So this is what the function actually looks like. So let's clip this in. Here's what the function actually looks like. Are we particularly interested in what this whole thing looks like? No. We're interested in what it looks like around what point. So what should we do at this point? Let's zoom box, and let's zoom around 1, 0. See the x value up there? I think you can see it. So we'll go from there. We'll go up. We'll go over. Here it is. Here's the function. Oh, okay. It's going up and down a bunch of times. That's nice. It's going around. Okay, there we go. So this is what the function looks like around the value we're trying to analyze. Great. So before you did anything, does it really help to see this picture? Absolutely. So this says Q is the point. X comma sine of 10 pi x. What does that? Where does Q live, therefore? Where does Q live? On the This is the function. This is a point where? On the function. That just represents any point on the function. This represents any point on what function? On y equals 10 pi x over x. 10 pi over x. That's it. That's what it equals. So what's the point that's anchored here? What point is anchored? 1, 0. So you're going, here's 1, 0. That's p. 1, comma 0. If we go back to our graph right here, and we use trace, this is actually one of the few times trace is actually useful. You hit trace. Let's find out where 1, 0 is. Where is 1, 0 going to be? X is, it's off the screen. Oh, it goes down, it goes up. Where's 1, 0? It's a little bit further, right? There's 1, 0 right there. Great. So that's where 1, 0 is. We're going from there to these values. Put the calculators down, stop looking at them. How many slopes of secant lines are we trying to find? No. How many is it asking us to find? 11 of them, right? Are you going to want to plug in each of them and do each of one of these manually? No. You make a table, but we need to make a table for the slope function. Let's make a table for the slope function. We're going from p, what's our q? X comma sine of pi over x. What's the slope? What's the slope from p to q? Someone raise their hand and tell me what the slope is. Raise your hand. It's in terms of x. There's nothing super complicated about this one. Yeah. What is it? What is slope? Tell me what the change in y is, Casey. Minus 0. What's the change in x, everybody? X minus. You have to do the same direction you did before. We went that way. Could you do the other way? It's the same thing. Totally fine. Is this okay? This represents the slope of any secant line where one point is stuck at 1, 0. And where could the other point be? Where can the other point be? Anywhere on the function, right? We want to make a table of values, though. What's our smallest x value right here on this list? You see how they purposely put it out of order? 0.5 is the smallest one, right? What should our delta be? No, it goes from 0.1 to 0.6 to 0.7. What should our delta be? 0.1. So if we go back to our equation right here, oh, and I've been on the whole time, which is fine. Y equals, that's the original function, right? What is our slope function again? It was y1. It was the original function divided by what? Divided by what? Divided by x minus 1. Do we care what it looks like? No, we want the table, right? But we want our table set to start where? 0.5. And our delta to be what?
Oh, 0.1.
We want it to start at 0.5 because that's the smallest one,
Okay,
right?
Yes.
We now do this. We ignore the first column because what's the first column? What is this? This is the function value. Do we care about the function value? No, we want the slope of the secant line. This is the slope of the secant line. When x is 0.5, what's the slope of the secant line? 0. When x is 0.6, what's the slope of the secant line? Negative 2.165. So let's clip this in. What should we do? We were too far away before, so what should we do? Go closer. So instead of 1.7, what should I choose? 1 oh, really close to, but we need to go under it.
Oh, then like 0.99.
Yeah, how about 0.99? Pretty good. And what should our delta be if that's it? 0.001. It has to be smaller or you'll skip really big, right? So now we do the table here. Look what happens over on the right. Does that look a little bit more calm? The idea of closeness is a completely relative thing. Kind of like the idea of heat, what's hot, what's cold. It seems pretty cold this morning, right? Minus 15. You know what the lowest recorded temperature in North America ever was? Like with wind chill? It's like top of Mount Washington was like negative 90 something, negative 80 something. The wind speeds on the top of Mount Washington are insane. You know what the coldest point on planet Earth is? There's a part of Antarctica that has these unique winds. You've seen this function before. Sine of 1 divided by x. Has anybody looked at that before? What zoom should I use? Zoom what? Yeah, zoom trig. Okay, it's nice and calm, and then it does this little flibbity-gibbet thing in the middle, right? The really interesting part looks like the middle part, right? What's 1 over a billion? What's that about? About 0, right? What's 1 over negative a billion? About 0, right? What's sine of 0? 0, thank you. So does it make sense that this thing is getting close to the x-axis as x gets big and x gets really negative? So it should come to 0, right? Because what's 1 over x as x gets huge? 0. What's sine of 0? It's getting smaller, right? It's getting smaller here. It's really interesting. So everybody, take a look at this picture and get in your mind what you think this will look like when I zoom in on it. Okay? You see what it looks like right there? It does this little like flibbity-gibbet thing, right? So I'm going to zoom in, and that's actually not the zoom function. I need to zoom box, right? Zoom box. And I'm going to, let's zoom like right here. So you have an idea of what it's supposed to look like, right? I mean, it clearly looks like it goes down, then up, then down, then up, right?
How would you just do that?
Zoom box.
That's so cool.
Wait a minute. There's more flibbity-gibbeting, right? So let's do this instead. Let's just do this. Let's check the window. We want to go around the y-axis, right? So let's go from, I don't know, negative 0.1 to 0.1. So I'm just squinching it this way. Does everybody understand what I'm doing? Yeah. I'm taking the middle slice. So I'm just looking at the middle, right? Wow! What the heck? It's going even crazier, right? So let's make it even more fun. Last thing here. Ready? Negative 0.001 to 0.001. Do you see those values? What is 1.5707963? Pi over 2. Zoom trig gives you nice trig values. But does it write pi over 2? No, it just writes. If you actually do that on the calculator, check this out. It just does it. So let's graph this and see what happens. Oh, man. Really? Now the big question is, why is it doing that? That's the big question. That's going to be the first part of your homework. I'm going to 2 of x squared. What does the output get infinitely close to as x goes to 2? 4. How do you know that? Just plug it in. You always check this first. I'm going to give you many ways of attacking limits. What's the first thing you always check? Plug it in. What we did on this one, yeah. Oh, almost. I should take that. Okay. When you plug in the number, sometimes you can and you will get an output. Can you plug in 2 in this one?
Yeah.
What do you get out? So as x gets arbitrarily close to 2, what does f of x get arbitrarily close to?
4.
We know that because you can plug it in. I have all these different complicated things to do, and so I can guarantee this will happen. You're going to try doing one of these complicated things. This is like in a couple weeks. You're going to go through tons of work. You're not going to be able to understand what to do, and then you're going to realize what? I could just plug the a value in, and I'm done. Always check that first. Always check that first. It's kind of mean, but that's going to happen. So, are you always going to be able to plug the number in? No. So here was the first example of x going to 1 of x plus 1 over x squared minus 1. Can you plug in 1? Why not? Divide by 0 error, right? So the first thing you do after you figure out that you can't plug the value in, the first thing you do is you try to get in as much trouble as you possibly can by not properly shutting off your phone. What do you always try to do? What do you always try to do? What's something you should always try to do? Simplify. What's one specific way you can simplify something like this? Always look to factor everything in your entire life, especially in math. What does the denominator factor into? Oh, okay. So the top is x plus 1. The numerator factors into x plus 1 times. What cancels? The x plus 1s cancel. Right? And what are you left with? 1 over... Oh, man. We can't finish it, can we? Why? Is there anything to simplify this with? Not really. Not really. What would you do at this point if you were trying to... What does the output look like on this if you actually were to look really close to 1? What could you do if you wanted to see what it looks like? If you want to see what a function looks like, what should you do? That's what we did. I was just telling us what we did there. If you want to see what a function looks like, what could you do? Graph. Where was that coming from? So theoretically, you could graph this. Let's come back to it. Let's come back to it. Let's say I changed it just a little tiny bit. Let's say I had limit as x goes to 1 of x minus 1 over x squared minus 1. What does that equal? That equals the limit as x goes to 1. This is a different question, remember. Different question. Of what? X minus 1 over what? X plus 1 times? What cancels? And you're left with the limit as x goes to 1 of 1 over x plus 1. What's that equal? 1/2. Because what can you now plug in? You can now plug in 1 into that one. We have only changed one thing. This function right here for part of it, as it gets really close to 1, does the function exist there? No, there's a hole. Over here, though, that same hole exists, but what have we done? We've filled it in. We filled it in. What's x minus 1 over x minus 1? That's equal to 1, right? But can you plug in 1 into that? No. The only thing multiplying by x minus 1 over x minus 1 does, the only thing it does is it takes out whatever the x value at 1 was. That's it. This is called a removable, someone said it back there, discontinuity. And what have we done to the removable discontinuity? We've filled it in. Now, can we evaluate it and find the limit? Absolutely. Does it matter if the value actually exists? Meaning, let's say I had this function, ready? And let's say I just deleted this point right here. That point doesn't exist. So I'm going to delete this. Let's say I do this to it. Let's go, pull that down. Eraser. I'm going to delete this one point right there. So this whole that function is there. This green function is f of x. And I'm going to say that point right there is 2, 4. What's the limit as x goes to 2 of f of x? 4. Does it matter that the point actually exists? No. Can you get arbitrarily close to 4 by getting arbitrarily close to 2? It doesn't matter. It absolutely doesn't matter. It actually doesn't matter what the function value is. Let's say the function was a dot right here. Does the limit change? Here's a bug traveling along this function value. You see the bug right here? As the bug gets infinitely close to the x value of 2, what's the y value you get infinitely close to? 4. Same bug over here. What's the y value you're going to get infinitely close to? 4. Does it matter where this point is? No, it does not. It can get infinitely close to a y value of 4, so the limit is said to be 4. It does not matter where the function value is. So, what's the first thing you do when you're trying to evaluate a limit? What do you look to do first? Plug in the a value. If you can plug it in, once you plug, done. You're done. If you can't plug it in, what's your next step? Sometimes it's graphing, or you try to what? Which is a form of doing, what's your goal when you're factoring? You're trying to simplify. So the next thing is, if you can't plug, try to simplify. If you get stuck, graph it. But let's go back to this one here. So this was slightly different. We got to this thing right here, right? So we're trying to answer this question. The limit as x goes to 1 of 1 over x minus 1. Is there anything we can do to simplify that thing? So do you know what that graph looks like? Do you remember what it looks like? I know you've looked at this before. Does anybody know what it looks like? Really? Okay, fine. 1 divided by x. What's a good zoom to start with if you have no idea what it looks like? Standard. Negative 10 to 10. So looks like this. It spikes down and it spikes up. You remember that, what it kind of looks like, right? Sure, kind of, maybe. So here we go, like this. So I'll make this for you. So here's this graph. Great. Everybody sees what it looks like? As x gets closer to 0, what does the output go to? So if I'm a bug, you ready? I'm going to try to do this. It's really hard to see the bug on this one because it's a bad color. But let's say I tried, I don't know, can you see that? No, you really can't see that. Ready? I'm going to make it. Here's the bug. You see it? The bug is moving on the function towards 0. What's the output going to? Yeah, the bug is over here. Where's it going? Positive infinity. The limit as x goes to 0 from the right is what? The limit as x goes to 0 from the left is equal to? So if you see this, what do you think the answer to this is? If I just said goes to 0, what does that equal? You say this. It does not exist. That's just technically what you say, everybody. If the limits are different, the limit is said to be it not exist. This is an extreme version because it goes to positive and negative infinity. What about this? This is the same x value right here, like x equals b, and this is g of x here, and this is also g of x. So it's the same function. It's right. Could that be a function? Could that be a piecewise function? Yeah, absolutely. Let's say that point there was, I don't know, 2, 6, and this point here was 2, 4. What's the limit of g of x as x goes to 2? No, it just says x goes to 2. What is it? How about 2 from the right? 4. What's the limit as x goes to 2 from the left? 6. So what do we say that the limit as x goes to 2 of g of x equals? Does not exist because the left and right hand limits are different. So again, does the value need to exist? No. Could there be an asymptote? Yes, absolutely. But you can come from the left or you can come from the right. But for the limit to exist, the left hand and the right hand limit have to be the same. Yay, the same. And we want it around 0. We want it to the left of 0. So how about negative 0.1? And what should the delta be? 0.01, or it's going to take too long to get there. And now what do? We look at table. Look at this thing. Look what's going on. What does it look like it's getting closer and closer to? Does it really look like it should be 1? Absolutely. So if we use our table on this, and even if you make a graph, it really looks like it should be 1. So one method, everybody, using your calculator, using a table. So this is number 1 here. So for number 1, here's the picture. Here's the table view. We could also make a graph of this if we wanted to. We just press Y, we press graph. What does this thing look like? It blips up. What does it go through? At 0, what does it cross? Yeah, so zoom box. What should there be at 1? There should be a hole. And are you generally going to see it on this kind of calculator?
Probably not.
Probably not, because the resolution is pretty bad, right? But what does it look like it's getting infinitely close to? It really looks like it's going to 1, right? Do you agree with that? Yeah. If you traced it, what would happen if I traced it around that? What would the calculator say the value is? It would give you error, exactly, because what's it doing at that point? It's a hole, exactly. So that's the first one. What about the second one here? What's the only thing I've changed? It's the limit as x goes to 0, but instead of sine x, what have I put on top? Pi x. So let's do the same exact analysis and see what happens. So instead of this, we're going to do, what was it? Sine of pi divided by x, and it's x goes to 0, right? We've changed very little. Do you agree? No, it doesn't seem like it. So let's do zoom. Hold on. Let's do zoom. We like trig, right?
Yeah.
This thing graphs really slowly and potentially freezes, so we'll just let that go.